So in this tutorial, we will talk about op-amp based circuits. But this, although this is tutorial, this is going to be more like lecture than tutorial. So I will cover few topics related with op-amp, and these topics will be helpful for you when you perform the basic electronics related experiment, hopefully in the next semester. Officially, it is allotted to the second semester, but if lab is held, then those experiments you will have to perform. And there are three experiments based on Opamp. So I thought that I will cover the key circuits which form the core of those experiments, especially the second and third one based on Opamp. So most of the Opamp circuits are analyzed using a concept called virtual short. So this is very important uh, concept, very useful, but this is valid only under certain conditions. So one should be very well aware what are those conditions which should satisfy in a given circuit before one can invoke this virtual short idea to simplify the analysis. In a simpler form, this is also called virtual ground. So you might have heard of this thing, virtual ground, but virtual short is generalization of this virtual ground concept. So suppose we have this op-amp based circuit. So here we have output and here we have input, and these two node voltages will be called VA minus and V plus. So in general, this V plus might be some non-zero voltage, but when we talk about virtual ground, so this implies that V plus is equal to 0. So this is the special case of virtual short. So this virtual short, this basically says that under certain condition, this Vi node voltage and V plus node voltages, they are going to be approximately equal. So can you point out what are the key requirements for this to happen? So we will try to relate these two voltages, and then we will see that what happens when we impose certain condition. For example, very high open loop gain for op-amp. So op-amp is characterized by various parameters, and one of the important parameters is called open loop gain. So loop means closed path. So in this second figure, you can see that there is no closed path. We are talking about only three voltages, VO, which is the output voltage, and V minus and V plus, which in general are on the input side. So can be called as the input voltages. So open loop gain A is defined as the output voltage divided by V plus minus V minus. And this leads to the equation for output. So this equation is always valid. You need not try to find certain suitable circumstances or condition in the op-amp for this to remain valid. And for ideal op-amp, this A is infinite for real, that means a practical op-amp which we encounter in lab, this A will be greater than typically 10 raised power 5. So this is very high gain. That means, for example, if we have this much of gain and this V plus V minus is equal to, say, 1 millivolt, this is a very small number, then you can quickly see that output is going to be 100 volt. And this is going to be very large voltage. Usually when we use op-amp in real life, this will be operated with the help of two DC supplies. Any amplifier requires DC supply. For example, C we have already seen, common emitter amplifier. So they will be typically plus minus 15 or 12 volts that will be required for this op-amp to operate as an amplifier. So you can see that even if we apply a very small voltage at the input, 1 millivolt, the output voltage, as per calculation, as per this fundamental equation, universal equation, is going to be 100 volt. But since this op-amp is operating on plus and minus 15 volt, so this output will never be greater than plus 15 or minus 15 volt. So even if I have a scenario where we have this kind of input, the output voltage will be plus 15 volt, the maximum of the DC voltage that has been supplied to the op-amp. And such type of outputs are called saturated output. That means this is the maximum output, you cannot go beyond this. And maximum is of course decided not by theory but by the these DC supplies. Okay, so as I pointed out, we want to know that what happens to this relation between V plus and V minus and when this is valid. So here you can see that if there is no loop connecting output to the input, say output to V minus, as you can see is the case here in the first figure, output is connected to V minus through Z2. So if there is a no loop, then equation 1 will always be valid, and whatever small input is there, it will be amplified to a very large extent. But now for figure 1, let us try to find out relation between V plus and V minus. And of course, we will keep in mind that A is the open loop gain is very large. So here we see that there are three paths meeting at V minus, one from input and other from output, and one to the V minus terminal of op-amp. But in the ideal op-amp, it is assumed that the input impedance is infinite. That means there is no current which enters into the op-amp. So these currents, I minus and I plus currents, they are zero. So for ideal op-amp, we not only have infinite gain, but also this I minus and I plus, they are equal to 0. And this is equivalent to saying that Z in impedance is infinite. So input impedance is infinite, there is no current enters into op-amp. So it is under this condition that we will try to find relation between V plus and V minus, and then try to see that what happens. So we can apply KCL at V minus node. So we have one current I1 here and we have another current I2. So at this node, what we get is I1 plus I2 is equal to 0. And I1 you can see is Vi minus V minus divided by Z1. And this one is V minus minus VO by Z2. So we basically want to relate V minus and V plus voltages. So we can eliminate this VO from equation number 1. So we will separate out the V plus and V minus. And before that, let us divide these impedances to get here Z2 by Z1 plus V minus plus AV minus minus AV plus is equal to 0. So we have this ratio Z2 by Z1 appearing here, and we can call this ratio as G. So we can separate out V minus term on one side. So we have G Vi minus G V minus plus 1 plus A V minus is equal to AV plus. So here, okay, so we can write V plus as G by A Vi minus G by A V minus plus 1 by A plus 1 V minus. So here we have a relation between V plus voltage and V minus voltages. So now if G is not comparable to A, the open loop gain, so then what we have is, and of course Vi is not too large, and in real life this second requirement will always be fulfilled, that the input voltage is not going to be very large. If it is very large, there is no point in amplifying it. So input will always be very small. So this condition is never going to be encountered in real life. And G, of course, also should not be too large. So if this is the case, then you can see that the V plus can be approximated to this first term is going to be 0 because denominator is too large. So here for this term also, denominator is too large, so it is going to be 0 plus 1 by A is of course 0. Then we have 1 and then we have V minus. So this gives rise to that V plus node voltage and V minus node voltages are going to be approximately equal to same. So key requirement is this: the ratio of the impedances in the loop and in the input side, they should not be too large. So G is Z2 by Z1. And of course, loop should be there. So this is one thing. Second is loop, and more precisely, negative feedback loop. Negative feedback means output is connected to the negative terminal of the op-amp. Right. So this condition is called virtual short. So as if V plus and V minus are shorted, and this is valid for first is negative feedback. That is there should be electrical path for current to flow between output and V minus. And this Z2 by Z1 not too large. So this is also should be satisfied. Then we can have virtual short, and if V plus is already equal to 0 in the circuit, then we have V minus approximately equal to 0. This is virtual ground. Okay, now we are going to use this idea to study two circuits, and these two circuits you will encounter in basic electronics lab. So first one is and integrator. So as the name suggests, this circuit integrates. So you will see that what is the function or what is the quantity which is integrated. So here you can see that Z2 is implemented using a capacitor, and numerical value of Z2 will be J omega C, and Z1 is a simple resistor. And this V plus node will be grounded in the simpler version. So now we have circuit, and we want to know what is the relation between this input, which will be in general time varying, and this output, which is also time varying. So here we can apply KCL at this V minus node. So here we see that there is a negative feedback. That means output is connected to V minus node through C, and the time varying current can flow through capacitor. Of course, if Vi is DC, then after certain moment, no current will flow through capacitor, and then there will be effectively no feedback path also, right? So that is why one has to see that there is a flow of current, not just connection. And if this is the case here, as has been shown, then Vi has to be a time varying. For DC, ultimately, this current is going to be 0 because capacitor will charge and it will not allow any current to flow through it. So now since negative feedback is there, and we will typically assume that this requirement, this ratio, is not too large is getting satisfied. So from virtual short, we know that this V minus is going to be 0 because V plus is grounded. So now we can write KCL very easily at V minus node. So we will have the current going towards V minus node as Vi divided by R, and the current coming from capacitor to V minus is going to be C dVo by dt. So here we see that dVo is equal to minus 1 by RC Vi dt. So we can now integrate it. So this will become from 0 to t, and this one will be voltage from 0 moment to voltage at t moment. So this simply becomes voltage at any moment minus voltage in the beginning. This right hand integration cannot be carried out unless we know the expression for this Vi. So here we can see that the output voltage is equal to, of course, a scale version determined by R and C, scale version of the integral of the input voltage, and plus a constant which will be the initial output voltage. So that is why this circuit is called integrator. And this circuit is used very often. So this virtual short idea has simplified this analysis. But if someone wants to carry out exact analysis, one can carry out without assuming this virtual short and the taking help of this universal equation, which is always valid, whether loop is there or not. So using this universal formula, one can find out what is the output, and there one can then impose the condition that gain A is very high, and one will invariably arrive at this equation, which when integrated leads to what we have here in equation number 2. Okay, so this is one of the applications. So similarly, there is a differentiator also, and for that we just interchange the location of R and C. So let me point out that Opamp is not the entity which is introducing this uh, functionality of integration or the operation of integration. Keep in mind that this operation of integration is arising because of the capacitor and because of the location from where we are tapping the output. We are taking output from here. So Opamp is only allowing us to achieve this specific relation, not the integration process. Similarly, here if we change the location of R and C, then one finds that the relation between Vi and Vo gets changed, and it will now involve the operation of differentiation. So we can see that now KCL V minus gives Vi minus V minus no, sorry, in this side, we will have C d Vi minus V minus by dt is equal to minus of Vo minus V minus by R. So we know that V minus is approximately equal to 0. So therefore, C dVi by dt is equal to minus Vo by R. So this says that output is minus RC dVi by dt. Of course, all these voltages, since the input is time varying, so output is also going to be time varying. So here we see that we have output which is derivative of the input. So in place of Z2, here you can see that now we have R, and in place of Z1 we have C. And typically these R, C and L are the entities which are used to implement any impedance. But this concept of virtual short is very general. In place of Z2, we need not have either L, C or R. We can have any other component also. So now we are going to use a diode at the location of Z2, and we will see that it leads to rectification. So we are now going to talk about precision rectifier. So before we go to this, we have already seen rectifier. So here we know that if we have input, a sinusoidal input like this, then in this case, you can see that the output is going to be of this form. So when we have positive input, diode will be forward bias and there will be current flowing through resistor. Diode will in fact act like a short circuit. So for this first half, the equivalent circuit is going to be like this. So that is why output is going to be equal to input. But for the second half, diode is going to reverse bias. It will be open circuited, and what you will get on the output is 0. So for this second half, the equivalent circuit is going to be like this. So here output is going to be 0. So can you point out what is the issue with this? So this input in general is going to be like this, A into sine omega t. So will it be able to rectify any sinusoid signal, or there will be some restriction, assuming that this diode is real? So what we have solved here is for ideal diode. But when we try to set up this circuit in the real life, this is going to be real diode. So for real diode, what will be the issue that we will face if we have a sinusoid signal like this?
Sir, it will have some resistance and the amplitude of voltage will be less than the input one.
Yes, that is of course true. But here keep in mind that for ideal, what we did, we replaced this diode by a short circuit. Short circuit. That is, so in real case, we will not be able to substitute it by short circuit. What you pointed out has to be taken care of and included here. But even before we decide whether diode is on or off, we have to see under which condition it will switch on and off. So for ideal diode, if let us say this VD is the voltage across diode. So for ideal diode, this VD is equal to how much? Even 10 raised power say plus minus 3. 1 millivolt will be enough to switch on the ideal diode, or even 10 raised power minus 5. You just need to have a very, very small positive voltage across it. So a very small positive voltage across ideal diode will switch it on. But when we set up this circuit, we will have to use a real diode. So for real diode, what should be VD so that it switches on? Hmm? What is the minimum forward bias voltage that should exist across a real diode for it to switch on? Will
For
it switch
ideal
on?
diodes, it will be
How much?
0 for ideal diodes.
0 for ideal diode, right? But for practical diode, I mean, real means
0.7 or 1.1 depends on the material.
how much? It will not be 0. It will not be very small. It will be typically 0.65 or sometime we say 0.7 volt if it is silicon diode, right? So if we have a silicon diode in real life, so diode will switch on only if it experiences a voltage greater than 0.7 volt. And 0.7 volt means 700 millivolt, right? So here you see that what we had said, even if it is 1 millivolt or even it 0.01 millivolt, ideal diode will switch on. But the real diode will switch on only if it is exposed or if it experiences more than 700 millivolt of voltage in the forward direction. So now you can see that this circuit, the rectifier circuit, is not going to work if we have a signal like this, say 0.3 sine omega t, right? So here the amplitude A is 0.3, 300 millivolt. So this, even if this 300 millivolt appears across this diode, it is less than 0.7 or 0.65, whatever you want to choose. So this diode is never going to switch on. So that means if say this is 0.3, then the output is always going to be 0. Output is always going to be 0 because diode will never be switched on. So this is for A is equal to 0.3. And this will be the case when uh, amplitude is less than 0.7. So even if you have 0.8, then what will happen is it will switch on only for a very small duration. So only a tip of the peak of the input will be allowed to appear on the output side. So even if you have, say, this kind of input, and this is, say, 0.9, so 0.7 will be here somewhere. So that means what will happen is, now you are going to get output which will be like this, and it will be 0, 0 for this portion, 0 for uh, remaining portion of the positive up, and the entire negative up. So here you can see that the output is clearly not the half-wave rectified version of the input, right? So this is the issue with the this simple rectifier. So precision rectifier tries to address this issue with the help of Opamp. So in the precision rectifier, we use an Opamp, and then we have a diode. And for this analysis, we will assume that diode is ideal, but you can take 0.7. It will have a little impact on the operation. But in fact, let us try to take it as 0.7. So we will now try to find the voltage at this node X and at node Y. So here also the virtual short can be applied even if we have diode in place of Z2. So keep in mind that Z2, or the loop, negative feedback loop, simply implies that there is a possibility of current flowing between node X and node Y. That means output and V minus node. So this is our input, and you can take this input now as 300 millivolt, the case which could not be handled by the simple rectifier. So here what will happen is, then we have a very small input here, and so when we switch it on, I mean, let us say that we have this setup, there is a switch here, and there is this input here. So the status of diode will be decided only when this output voltage has been determined, and uh, uh, it experiences either a forward bias voltage or uh, a reverse bias voltage. For that case, it will be switched off. So when you close this switch, what will happen is, in the beginning, there will be some positive voltage that will appear here because of this Vi. So Vx is going to be in the beginning some certain small positive voltage, and we still don't know what is output. So we know that output will be determined by A into V plus minus V minus, and V plus node is 0. So output is going to be minus A into V minus. And in real life, A is going to be 10 raised to 5 or more, but in ideal case, A is going to be very high. So you can see that even if a very small positive voltage appears at node X, the output is going to be significantly large negative. So output is going to be large negative. So what happens is that as soon as you close this switch, that means input is applied, we have this scenario. a positive voltage at the cathode and negative voltage at the anode of the this diode. So this diode becomes reverse bias. So it is reverse bias in the entire positive half. So if it is reverse bias, the equivalent circuit is so for this half, the equivalent circuit is going to be like this. So this is going to be open, and we know that there is going to be no current into op-amp, and this current is also going to be 0. So this Vx voltage is going to be same as Vi. And this Y node voltage will be determined by Vo is equal to minus A Vx. And this is going to be large negative. So typically this voltage, output voltage, is either equal to plus 15 volt or minus 15 volt. This is the largest or extreme values possible. So it will turn out that this VO for this case is going to be minus 15 volts. Sometimes we use plus minus 12 volts, but they will always be symmetrical, whatever may be the value. So here we see that for the first half of the input, even if it is 300 millivolt, the output is going to be 0. Sorry, equal to the input. So output is same as output means X. So output does not mean that we have to always take output from here. As you can see that in this case, we are able to get rectified signal from node V minus, which we are calling Vx. So for this case, Vx is going to be the node of interest. So that is why we will be calling that as the output. But usual output is also there, but it gives a constant 15 volt. Vy, which is also equal to Vo. So it is giving minus 15 volts. Okay, so now let us see what happens during the negative half of the input here. So when Vi is less than 0, so this implies that Vx, again, you start the analysis from here, that Vi is negative. So this switch is closed at this moment. So what happens is Vx is also negative, maybe very small. But as Vi goes up, this is also going to grow up in magnitude. So when Vx grows up, Vo here, you can see that is given by this expression. So here, let us plot case 2. Vi is negative, implies that Vx is negative, and growing in negative direction or magnitude, but negative sign with Vi. So here output is minus a Vx. So since x is negative, this implies that Vo is positive. And since it is multiplied by a, Vx is multiplied by a to produce Vo, so this is going to be very large. So this will be definitely larger than 0.7. So in this case, what we see is this scenario. So here we will have plus 15 or uh, maybe smaller but sufficiently large voltage. So we have positive voltage here and we have negative here because Vi itself is negative. So this implies forward bias diode. So diode will get a forward bias. So if it is not forward bias, this voltage will keep on increasing till it achieves the 15 volts, because here you can see that Vi is increasing. So it will definitely switch on. There will definitely come a moment when this Vd is greater than 0.7. So once it is greater than 0.7, we know that diode is forward bias, and in that case, it can be replaced by this circuit or 0.7 volt source. Here. So now you can see that there will be current flowing through this. Diode is forward bias, so it will allow this current to flow. So this implies negative feedback exists. So this implies virtual short. So this implies Vx to be 0 because V plus is equal to 0. And since Vx is 0, so here you can see that Vo is going to be Vx plus 0.7 volt. And Vx is 0, so this is 0.7 volt. So Vo is going to be 0.7 volt. So it is going to be very small, 0.7 volt. Here we have minus 15 volt. And Vx is 0. So this is 0 volt. And this is same as Vi. So we see that node X, which is V minus node voltage, is half a rectified version of the input, even if the input is very small, 300 millivolt. And this is why, because output is A times that of the Vx. So it is A which is able to produce large voltage across the diode, large positive voltage or large negative voltage, even with very small external input voltage. So that is why this circuit is capable of rectifying even a very small input signal. So as I pointed out, this is going to form the core of one of the experiments. So now onwards, whenever you have any precision rectifier circuit, you can take a shortcut. You just see that whether diode is going to get forward bias or not. And for checking whether it is going to be forward bias or reverse bias, you just try to see the polarity of this output voltage and this voltage, or rather this input. So we know that if this is negative, this will be negative because input is negative, and if we have negative input, this is going to be positive. So we will of course have this polarity of the voltage across diode, and diode will be forward bias. Similarly, if we have positive here, so this is going to be positive, that will give rise to negative output, and then we will have this polarity, and this polarity will ensure a reverse bias diode. So diode will be open, no feedback loop, and then virtual short will not be applicable, and then you can estimate what will be Vx. So you just pay attention to the polarity of input, and using this you can find the polarity of output, and then guess. You need not do the precise calculation to see that there is enough voltage. Typically it will be there, but in real life one might have to be careful, do the calculation, and to see that indeed at least 0.7 volt forward bias is appearing across the diode. Right, so do you have any query to ask? Now we can see the different version of this. So here we can reverse the orientation of diode. So we again have sinusoidal input. So can you now tell what will be Vx? So as I pointed out, just follow these two things. Polarity of Vx is same as that of Vi. So this is one fact that you will have to keep in mind. So using this fact, you can find out what is the polarity of Vx. Polarity of Vo is opposite to that of Vx or Vi. So choose the polarity of Vi, find out the polarity of Vx, which will be same, and the polarity of Vy is going to be reverse of that, opposite of that. So based on that, you can find out the polarity of voltage across diode. If the polarity is forward bias positive, then diode is can be taken as forward bias and substituted by a short circuit or maybe 0.7 volt source. If the polarity of VD is negative, then substitute diode by open circuit. And for each of the two cases, determine Vx and if required Vy also. So you just keep these facts in mind, and then you will be able to solve. Determine the forward bias or bias condition, rather determine the bias condition of the diode, whether it is forward bias or reverse bias. So what will be Vx voltage during first half of the input? So during first half, you can see that this is positive. So this is also going to be positive, and Vy is going to be negative. So during this half, diode will experience this kind of voltage. So this implies this is going to be forward bias. So this implies virtual short. So virtual short implies Vx is equal to 0. So during positive half, you are going to get 0 output. And during negative half, we have negative here. So this is going to be negative. Output is going to be positive. So polarity is going to be negative and positive like this. So VD is going to be negative. So this case then implies reverse bias. So this implies open. That means no feedback. So path is broken. That means no virtual short. So this implies Vx is going to be same as Vi. So in this case, we are going to get this kind of output. So we again have half rectification, but this time we are getting the second half of the input. And those who are interested in reading this topic, they can read it from Fundamentals of Microelectronics by Behjad Rajavi. And you can see the section 8.3 of this. In fact, 8.3.1.
Okay. Please once also draw the output voltage of the last circuit you shown.
Okay. So this output you want to see once again. So you want Vx or Vy?
Sir, Vy.
Vy. Yes. So for okay. So during the first half, you can see that there is a virtual short, right? So this diode is also acting like a short circuit. But if you want to include its voltage effect, then we can have this voltage source in place of diode during the uh, first half of the input. Right. So we have already concluded that for first half, Vx is 0 because of virtual short or virtual ground. Right. Now you can see that Vy is nothing but Vx minus 0.7 volt, and Vx is 0. So this is going to be minus 0.7 volt Vy. So if we plot Vy, so Vy is going to be minus 0.7 volt, right? Now, what about the second half? For second half, we see that Vx is negative, right? So for second half, we have this circuit. Diode is reverse bias. Diode is open circuited. So here we see that Vx is equal to Vi, and Vy, we know that it is minus A into Vx. So since A is ideally infinite or practically very large, right? So the Vy is going to be very large and negative. So in real life, uh, this Vy, we know that is going to be maximum of minus 15 volts. So this is the maximum voltage we will get. So Vy is going to be minus 15 volt. No, sorry, Vx is negative, so this is going to be very large positive voltage. Here, Vx is negative, so this is going to be very large and positive. And the maximum positive voltage that you can get in real life is plus 15 volt. So Vy is going to be like this. So this plus 15 volt will be called as the saturated output.
Sir, in that, in starting of this, you wrote Vx is equals to Vi down the page. Why Vx is equals to Vi?
Here you see that in this circuit, what will happen? This is open. So this current will be 0, right? And this current is 0 all the time for ideal diode. So that means there is no current flowing from Vi. This input current is 0. So
Okay,
this
sir.
implies Vx is equal to Vi.
Okay, sir. Thank you, sir.
Hmm.